yesterday, and I think there are 2 talks yesterday. I think actually we have a good representation right now. This is my first Derbycon actually, so that's pretty cool, and I'm liking things so far. All right, moving on. So what this talk is about generally, we're going to talk a little bit about how random number generators are implemented in some cases, how to predict those things. I'm going to release a tool that will help facilitate that prediction, and we're going to talk about how you can leverage the predictability of some random number generators into actual attacks against real-world systems. And then lastly, we're going to wrap things up with a little bit of an explanation of how you can mitigate this kind of predictability. How can you avoid your RNGs being predicted and people attacking you? So what I'm not going to tell you, I'm going to assume that everyone here knows not to use RAND to generate their private keys. Your private keys need to be like strongly cryptographically secure. So I'm assuming that everyone uses like OpenSSL or something reasonably decent to do that. No one probably writes little Python script to generate their private keys. I assume that you use strong cryptographic security. And I'm not going to talk about statistical attacks. It is possible that you can have statistical anomalies in an RNG that will, an attacker could leverage. For example, if you had a gambling website, it would be pretty relevant if the numbers that you generated had some statistical anomaly that an attacker could be like, oh, if I bet like this, then I make millions of dollars from you. So there definitely are ways that there could be, kinds of problems like that, but it's not the kind of thing that we're really going to be focusing on very much. Excuse me. So before we really get into things, I'm going to have to cover a little bit. I'm going to assume that you know basically nothing about random number generators. So I'm going to go through a little bit about the difference between cryptographically secure and non-cryptographically secure ones, in case you're totally unfamiliar with that, before we get into the rest of the talk. So cryptographically secure RNGs are characterized by 3 properties, right? The first of which is the most obvious. They must be unpredictable. So given any number of outputs from the RNG, it must be impossible to say what the next one will be. That's probably the most evident thing about cryptographic security. The second one is a little bit stranger. If someone is able to compromise your system, so they have total control over everything, they can make the RNG output whatever they want, they've pwned you completely, it still must be impossible for them to recover prior values output by the RNG. It'd be really bad if I could break into your system and recover your RSA private key you generated last week. That'd be pretty rough. So cryptographically secure RNGs, that needs to be impossible. And lastly, there are statistical requirements that we're not going to get into, but suffice it to say, it must be fairly difficult to distinguish outputs from such a cryptographically secure RNG from just random data, right? So if you look at this and you're like, I don't know if this is just the cosmic microwave background or what, or if it's actually a random number generator. It should be really hard to tell the difference. Non-cryptographically secure RNGs fail in one of these 3 categories. Either you can predict the following numbers, you can recover prior ones, or they're very obviously not truly random. So, for example, one might always output even numbers. Even if it's unpredictable, it's still always even, so obviously that's not just like a random thing. It's it's an output from some kind of algorithm. Typically, most actual RNGs you're likely to use that are not secure fail in at least 2 of these areas. In many cases, they fail in all 3. So they're not truly random, they're predictable, and you can recover prior outputs. So that's pretty rough. And the real problem here is that while languages and platforms provide a lot of different ways to generate RNGs, they are almost always not secure by default. Usually you have to learn more about cryptographic security and you have to reach for the tools to generate secure, unpredictable random numbers. Almost always they are predictable by default. And I say that to the extreme that I am unable to find a language that by default gives you cryptographically secure RNGs. Almost always it is something that you can usually fairly easily, trivially predict. And attackers can definitely use this. If you're doing something like generating session IDs with a trivially predictable value, that's obviously a problem. Hopefully you're not doing something that obvious, but there are more subtle ways that you can use non-secure RNGs. So we're going to use a little bit of a demo for the uninitiated. If you don't know anything about C, this just says there is a default C random number generator, and so you can call srand and you kind of initialize it with a value, and then you call rand to get a value from it. So this just seeds the thing with some input that I'm going to ask you guys for, so that there's no sleight of hand going on here. And then I'm going to output 50 values from it, and we're going to do a little demonstration with predictability. Hopefully everything is visible here, and I'm not standing in the way. Am I, like, in the middle of the path? No, okay, cool stuff. So, all right. This, cat. C. All right, so that's that same program. Yeah. See, that's what people told me I could do that. I'm coming from a Linux background, you can probably tell. So what do you guys, can you throw out a number that is an unsigned integer range? Don't try to underflow me or something. I'll be annoyed. Pick a number. Come on. Anybody. Any number.
127.
Sweet. Boom. All right. So we've got some random numbers that are based on the seed 127. I'm going to do the bizarre nonsense you have to do in the Windows command prompt to copy this. Boom. Copied. All right. 4C is a tool I'm going to talk about here in a little while. But you can see the help string for it here. MSVC is the name, if you're unaware of the kind of Microsoft compiler. Now, you'll notice here that I copied the first 3 values. And that should be a little disconcerting, because I'm about to predict... Man, the .exe thing just kills me. You'll notice that these are the same values, right? The ones that follow, so I said, you got these 3 numbers. The next one's going to be 11,053, and sure enough, 11,053 is in fact the, right there, yeah, come on, right there, is in fact the subsequent number. And this should be kind of disconcerting to you, unless, you're like, well, RAND's just obviously not cryptographically secure. But I mean, with 3 outputs, you can predict not just the subsequent 10, but the subsequent 100, or if you just remove this, every value that will ever be outputted by that thing. So once you have 3, you know every future one that will ever be predicted for the rest of time. And that's kind of an issue, and it's not remotely unique to the Visual Studio's RAND in C. This is a really common problem across basically all non-secure RNGs. Once you know a little bit about it, usually far less than people suspect, you can predict all future ones. And that's kind of an issue. So in this particular case, why does this work? I promise there won't be a lot of math. All right, I'm going to go through the equation. Everybody calm down, stay in your seats. So no one's running for the door, that's good. So X in this case is just an output from the RNG, simple enough, right? So X of n is the nth output, X of n plus 1 is the next output. So all this says is the next output from the RNG is just whatever the last one was, times some constant A, plus some constant C, modulus some constant M. And that should make you pause, because that means if you have any output, you just feed it through this thing in a loop, and you can just keep doing it forever, and you can get the next one, and the one after that, and the one after that, and so on and so forth for the rest of time. And that's, these are constants here. And those are trivially findable with reverse engineering, or they're usually, fairly often, they're just documented. You can just read through the Java documentation, and they say, hey, our RAND uses those constants, here they are, and you can just feed them into this thing and predict the future ones. These are generally called linear congruential generators, which is quite a mouthful, so I'm going to refer to them as LCGs. And they're used in the defaults for everything from RAND in C and C++ to PHP to nextInt in Java. The MySQL one uses a fairly similar mechanism. And all of them have this trivial predictability. In addition to that, they also have obviously bad statistical characteristics, because those are points generated from an LCG, and they just make lines in 3-dimensional space. Like, you can just pick some points, and they just make a bunch of lines. So obviously, if you just graph some outputs from it, it has very poor statistical characteristics. That is obviously not truly random. If I get entropy, it doesn't look like that. There are, of course, other things that are not cryptographically secure, but are not LCGs. A common one you may have heard of is Mercian Twister. The cloud of points here is generated with Python's random, which is a Mercian Twister implementation. And so it obviously looks a bit more random. It has better statistical qualities. We're not going to get into what exactly that means, but suffice to say, it doesn't make a bunch of lines. But they are still predictable. You just need a few more. You need 624 outputs to predict all future ones, which that certainly makes some attacks not feasible, but for sure there are situations where you can still get 624 outputs. And there are other ones like additive feedback, which is just sort of this weird thing that glibc uses, and it's a huge pain to implement. Trust me. So, tool release, the exciting bit of the presentation. So, you don't really want to have to do all the math every time you want to predict these things, because it's not quite as trivial as I made it seem earlier with that thing. Usually they shift away a bunch of bits in an effort to obfuscate things, and they tend to do modulus, and if it's PHP, the devs have no idea what they're doing, so they just do some random nonsense, and it's a huge pain to reverse. So, I made a tool that does it for you, currently supporting PHP, Java, glibc, MSVC's RAND, and MySQL. So that's a fair variety. I plan on adding more of that to the future. I'll probably do Mercy and Twister next because it's kind of the big, like, people think that they're making stuff more secure when they use Mercy and Twister, which is not true. So I'll probably do Python next, and Mercy and Twister will give me a bunch of other things like MTRand and PHP and such. And so that's Foresight on GitHub there. That link will be at the end as well. So if you want to take a picture or whatever, you can wait, and it'll work. But I appreciate that not everybody's a programmer. They don't want to deal with like using Python libraries to do things. So there's also a command line interface called forC, which is in that same repository. So if you wanted to, for example, predict the output from the rand_r function in glibc. So say you do some reverse engineering and you're like, well, I know they compiled this with GCC, and I see they're using rand_r. So I know I've got these outputs, but I want to know what the next one is. Well, you can just drop into the CLI interface and say, this command line interface, and you say forC glibc rand_r-o, and then the outputs, and it'll give you all future outputs from the thing. So that's, hopefully fairly handy for you. PHP has, it has like their rand function takes like an upper and lower bound. So you can say like, I want random numbers between 1 and 100. So if you have that situation, just put -r 1 100, it'll figure it out. If you want to limit the outputs, which you probably do, because otherwise you get that gigantic stream of scrolling stuff for the rest forever, you can just limit it with -c 100. And by pure coincidence, happy coincidence, doing this kind of predictability like requires that you basically implement the RNG that they're using in whatever language you're using. So you can also just pass a seed and get all future ones if you just happen to know the seed. Hopefully you don't. Hopefully nobody's giving away the seed, but and it's just a nice little feature you can add there. And we'll see actually a case where someone does give away the seed in a second. Right now. So examples from the wild. This is actual stuff that people have done. Again, I'm going to walk through this assuming that you don't know anything about code and you can't read PHP. Good if you can't read PHP, because it's terrible. So again, much like C, there's kind of this srand rand thing going on in PHP, and you can seed random what this guy does. This is real code. It's now been patched, so you can't just like break this dude's stuff. But this is used to generate a CAPTCHA, and it was fairly widely used. Like I've obfuscated things a little bit, but like, I mean, I did some searches, and it was like a few thousand websites that just use this as their CAPTCHA, and it is completely worthless because they go, okay, we're going to seed the random number generator with the time, and then they generated rand in a loop here. I cut it out because it was a bunch of crap. And then they make a URL which ends with the time that they used in the seed, which is not as good. It's kind of problematic. So you don't even have to use Python for this. You can just drop the thing in, and there you go. You just say rand, and I know the seed, so then you put in the time that they used as the seed, and you're done. And that'll give you all the future ones. They patched this once before I talked to them about it. They patched this once very recently, and they said, we're going to remove the seed. Right? We're not going to seed rand. And that's not as dumb as it might seem, because PHP implicitly seeds rand with the combination of the processor ID and time and some stuff that you can't predict. But they're still generating the values with rand, which means all you need to do is break one CAPTCHA by hand, and you recover the state of the RNG, and then you just predict all future ones, and that's like 5 lines of Python. So you just say, basically, from foresight.php import rand from outputs, and then the outputs, and it'll give you all the future ones. So again, that doesn't actually solve the problem. I gave them another patch. Unfortunately, they want to target PHP 5, which doesn't really have a like built-in secure thing. So I said use MTRand, which is Mercy and Twister, which is, I guess, as good as you can get. It was PHP, so I didn't really care. Now a C one that's less bad. This was used in kind of a pastebin style thing. So like you upload a file to it, and it gives you like a URL that's kind of implicitly the access control for the site, because like they don't want people to have to make accounts to log in, but also everything's not really public. Like you can't, there's not like a good way to like crawl that or anything. So what they do here is they just call rand_r in a loop, and they modulus it by the link. They've got a big list of these letters, and they just say, we're going to call rand_r in a loop and choose the letters. And there's obviously some logic that I cut out that prevents you from selecting previously made. Obviously, you could happen to generate one that was already used, but they were smart enough to actually like do that correctly. But clearly that still doesn't actually work, because all I have to do is upload one thing, see the URL that I get back, what letters were chosen, and I recover the RNG, and then I can predict all future ones. So that's, again, kind of a problem. Once I've uploaded one thing to the file, I can recover the URL of everybody else that ever will upload it. So again, just glibc, import rand_r from outputs. You're seeing a pattern here. There's a flag here that you can say output modulus, so if you just know the Sterling, that's always going to be 52, because it's just like upper and lowercase letters. And then like, there you go. So you just stick that in there and from outputs. That's the last code sample, so if you're asleep because you don't care about C, then you're good. No more code. So how do you prevent it? Prevention, this is pretty low-hanging fruit, right? I'm not showing you any crazy, like, oh, I hacked into their stuff and I found, like, race conditions on their IDs, and, like, it's just, I did some GitHub searches for RAND and shows the first few things, because, like, everyone messes this up, and I was spending my time doing the math to make the thing work, rather than, like, trying to find a lead hack. I trust you guys can find lead hacks, and I probably will later. But the problem here is that people inadvertently rely on unpredictability. I think that's, like, the greater problem, right? They don't really think about it, and they just see the spec says it doesn't have to be cryptographically secure, right? There's like, well, whatever, the spec says you just need to generate some random values, and it's got to be uniformly distributed across this range, right? It's not a secret. Anything that's not a secret, people treat like you don't need to use a cryptographically secure RNG. The problem is your implementation may often implicitly require that the thing be unpredictable. For example, suppose you have a system that generates user IDs within some range, and it just uses like Mercy and Twister, right? Mercy and Twister, you need 624 outputs. That's a few, but it's not like enough to actually prevent me from recovering anything. So what happens then when your system's about to generate a user ID? I predict what the user ID is going to be, and I send you a request with that user ID at the same time that you're about to generate it. Is there a race condition? I have no idea. Probably your testers have no idea. Probably no one ever tested for that, because that's a bunch of crazy nonsense. Because nobody thinks about, like, oh, what if they predict my random number generator and then they put in an ID attack? Like, that's just a bunch of convoluted nonsense, but it's, like, definitely doable. Like, that's an interesting avenue of attack that I think is, like, entirely unused now, because people don't really consider the practical. It's treated like an academic exercise. When I disclose some of these vulnerabilities to people, a response that I got almost verbatim from one person was, I don't know how practical that attack would be, right? He's using RAND, and he's like, I'm like, well, that's going to be really easily predictable. And he says, that's almost an academic exercise. No one really knows, like, there's no tool to do that. And now there is, so he can't claim it's an academic exercise anymore, because I can link to my GitHub. And I'm going to, actually, after this. I told him I was going to release a tool. I'm going to send him a link. So the solution here is fairly straightforward. Just use a cryptographically secure RNG wherever you can. If you haven't benchmarked and found out that you can't use a cryptographically secure RNG, just don't do that. Just use a cryptographically secure RNG unless you know that you can't. Because seriously, there's probably some nonsense I can do with race conditions, or, I mean, there's just no, like, you have no, there's so hard to test that sort of thing. How are you going to test, like, what happens when an ID is sent that is, like, supposed to be generated in a second? That's just crazy. So basically every platform has some way to do this. It's just marginally more difficult. You know, on Linux, you can read from dev-urandom. I'm not going to get into the difference between dev-urandom and dev-random. Just use dev-urandom. It's just better. Arc for random is like a BSD thing. RAND device is OpenSSL. RAND-S on Windows, apparently. I haven't really used it, but it's cryptographically secure, I guess. There are, performance implications. Random bytes is pretty fast. OpenSSL does this pretty quickly. Dev-urandom is unfortunately a bit slower, but I mean, just profile and see what's going on. I hesitate to say it, but otherwise, use Mercy and Twister. If you've benchmarked and you absolutely cannot use a cryptographically secure one, use Mercy and Twister. It requires a bunch of outputs to predict and has very nice statistical characteristics. So that's probably your next best bet to cryptographic security, but seriously, you should really benchmark things. And there's the URL at the bottom. If you want to go check it out. Star things, hint, hint. But anybody have any questions? I don't know how much time I have left. Yeah, 5 minutes. Questions? I've explained everything perfectly, I'm sure.
Do you need to add sequential?
So at the moment, yes, but it depends on the RNG. For LCGs, in principle, you don't at all. So that's probably going to be version 1.1 is just, I'm going to add that because it's super easy. It's basically just, you advance you can put like an underscore where you don't know a value, and there's no reason that wouldn't work at all. It's more problematic with Mercy and Twister because there's just like an array of values, and it's a little weird, but with like LCGs and some of the other ones, it would be no problem at all to not have consecutive values.
And would you need to know, if you didn't know the values between two values, would you need to know how many possible values are unknown?
I would have to think more about the performance implications of it. You could not, by just trying, like, you could say basically assume there's one thing between it and see if it works out.
Yeah.
And I mean, it runs in less than a second, so I mean, probably you could afford to do it, for assuming you have some idea. It's not like there aren't a million between it, if like probably there are only like 10 or so between it. For some of them, yeah, you're basically brute forcing like 2 to the 16, which is just like nothing on a modern computer. So I mean, it's not a big deal to try that. So that's definitely something, that kind of like, a less restrictive interface is definitely something I want to add in the future.
Yeah, I was just thinking, like, if you were,
For sure, yeah.
It's been given out between
Yeah.
the two, two lending.
Is that about going back? And you kind of mentioned.
Yeah, recovering prior outputs. Yeah, it's a very similar kind of thing. I focused more on getting like a wider range of like platform supported rather than like one thing and being able to go forward and backward. But yeah, for some of them you definitely can also go backwards, like LCGs. You can.
If you went backwards though, it also goes to help your conversation with the one person that said it's kind of academic, because if you can go back and find a few the past ones.
Yeah, that's true. All right. Sweet. Thank you. Mhm.
Well, we got 3 minutes, so as soon as we get the cue to start.
Start this one up yet?
Not yet.
They're gonna reset the recording stuff.
Okay.
Okay.
Go.
Maybe down to Stable16, so if you sit in here for a while and just. It's still recording. Who's this? Actually, what are those names?
This is Ben and Amber.
Ben.
Ben and Amber, homebrewing for hackers.
That's not them. That's Adam. See, that's Adam.
That was the previous